All right, good afternoon, everybody. Let's begin our lecture in mechanics. Now, in a previous lecture, we discussed about, we first discussed about rotation, right? And we discussed rotation making use of several angular quantities. Instead of using the linear quantities, we use the angular quantities. Let's have a brief review of what we have introduced to you. The angular displacement. The angular displacement is the angle that the object turns through. And the rate of change of the angular displacement, is known as the angular velocity. Okay, so omega is d theta dt. Okay, and also we are dealing with angular acceleration. The angular acceleration is the rate of change of the angular velocity. Okay, and if you like, you can write in terms of the angular displacement as the second derivative of theta with respect to time. Okay, now so each of this quantity actually has the one-dimensional counterparts. Each of the quantity correspond to the same quantity in the one-dimensional motion. For example, the angle here turned through by the motion of the object is analogous to the linear position of an object in one-dimensional motion. So theta corresponds to x, okay, in one-dimensional motion. And the angular velocity omega, because it's the theta dt, it corresponding to the velocity in one-dimensional motion. Okay, so omega correspond to v in the one-dimensional motion. Okay, and also you have the omega dt, the rate of change of the angular velocity, as the angular acceleration. So if you replace the omega with v in one-dimensional motion, you have the linear acceleration. So the angular acceleration in the rotational motion will correspond to the linear acceleration a in one-dimensional motion. So each of the angular quantity actually has its linear motion counterparts. And the mathematical relation between this quantity are exactly the same as in the one-dimensional motion. Okay, and that's why if you are dealing with, for example, a constant angular acceleration motion, so where alpha is a constant, you don't need to do don't need to solve the equation again, because you already have solved it for linear motion. Okay, the mathematical structure of the linear motion is exactly identical to the mathematical structure for the rotational motion. So if you are studying a motion with a constant alpha, that corresponding to a motion with constant a, right, for the linear case. So you can use exactly what you got, the result what you got from the linear case, and replace the quantity with the angular counterparts to arrive at the angular relationship. So that's exactly what we are going to do. Now, I think you are very familiar with the uniform accelerated motion. You learned it in high school. You have 4 formulas, right? V equal to u plus at, x equal to ut plus half at squared, v squared minus u squared equal to 2ax, and x is equal to half of v plus u multiplied by t, right? These are the equation of motion with constant acceleration. How about the equation of motion for a constant angular acceleration alpha? Well, that corresponds exactly to the linear case, right? You simply can change, for example, the a to alpha in the equation. And for the initial velocity in the linear case, you change it to the initial angular velocity in the angular case. So v is so the u now become omega naught. We use a subscript naught o 0 to denote the initial value of the angular velocity. And the final speed, final velocity v now become the final angular velocity omega. Okay, so v become omega, and u become omega naught. Okay. Now, the x, of course, now become theta, right? Now become theta. The linear position now become the angular position. Okay, so everything carry over to the angular case. Okay, so you have this formula. If you are dealing with a motion with constant alpha, you can directly apply this formula. Okay, and the corresponding between these two set of equations, it provides an easy method for you to memorize this set of formula. Okay, because you simply can translate the linear motion variable to the angular motion variable, and everything will apply. Okay, but I emphasize again that only applies to a constant alpha motion, a motion with constant angular acceleration. Okay. Now let's have a brief review of a circular motion before proceeding. It has quite a long time when we discuss about circular motion. So at this stage, I think it would be good to have a brief review of it before proceeding further to the rotation of a rigid body. Okay. For a particle, for a single particle moving around in a circle, we describe the motion by this vector, right? We assume that since we assume that this is a uniform circular motion, the angle theta that the position vector makes with the x-axis is equal to omega t, where omega is the angular velocity. Okay. And in terms of this angle theta or omega t, I can write the position vector in terms of the I and j component. The x component or the I component is r cosine of theta or r cosine omega t, which is this line, right? Sorry. And the y component is r sine theta, which is the vertical line here, or r sine omega t. Okay. And the velocity, the linear velocity and the linear acceleration, they can be found by direct differentiation of the displacement of the position of the particle. Okay. So a straightforward differentiation will lead to this result. You change the cosine into a minus sign, and don't forget when you apply the chain rule in the differentiation, it contains a term that is the differentiation of omega t with respect to t, and that gives you a factor of omega. So when you differentiate the sine and the cosine with the argument omega t, you always get an additional factor of omega. Okay, so we extract this factor out, and the cosine become a minus sign, and the sine become a cosine in the differentiation. And the second differentiation will lead us to the acceleration, right? So the minus sign now become go back to cosine again. And I take out the minus sign and also the other factor of omega. So I have omega squared r, okay? And the cosine here become minus sign. Again, I take out the minus sign, okay? So you can see this brackets together with the r, it is just the original position vector. So I can denote it by the r vector, okay? So that is the relationship between the acceleration and the position of vector of the object. They are in opposite direction. The radial vector, the position vector direct outwards, and the acceleration vector direct inwards because of this minus sign, right? So that is what we call centripetal acceleration. And the centripetal acceleration is related to omega and r by a equal to omega squared r, okay, with a minus sign. And from the velocity equation, we can see that the guy inside the bracket is a unit vector. It's a vector that is tangential to the circle. So in terms of magnitude, the linear velocity and the angular velocity, they are related by v equal to r omega. Okay, so remember these two relationships when we are going to use them to transform our motion into the rotational cases. Okay. And we also will be dealing with, for the previous example, we are dealing with a constant angular speed, right? this formula for the constant angular speed. But in our discussion, we will encounter the situation of a variable angular velocity. So there's an angular acceleration, okay? And the angular acceleration itself may not be constant. Okay, so that is a very complicated situation, but you still have the basic thing correct. For example, the centripetal acceleration is still given by minus omega squared r. Now, this result is independent on whether the angular velocity is constant or not. Even the angular velocity is not constant, there is still a component of the acceleration that is towards the center of the circle. And that is the centripetal acceleration. And it's also given by minus omega squared r, where omega is, of course, the angular velocity at that instant, at the instant that you're concerned. Okay. So this formula still holds. But you notice that I deliberately denote it by the subscript r because there's another component of the acceleration. Now for uniform circular motion, this is the only component for the acceleration. But for a circular motion with changing speed, with changing angular velocity, then you have a tangential component of acceleration. Okay, and the tangential component of acceleration is given by the rate of change of the speed. Okay, because this is in the tangential direction, right? And the speed is the equal to r omega. Okay, but r is a constant for circular motion. So the time derivative acts on the angular velocity, which becomes the angular acceleration. So the tangential component of the acceleration is equal to the radius of the circle multiplied by the angular acceleration. Okay. So it's just like V equal to r omega. Okay. Now for the speed, the linear speed and the angular velocity, they are related in this way, right? V equal to r omega. Now we have the acceleration. The tangential component of the acceleration is also related to the angular acceleration alpha in the same way. You can notice that these two formulas exactly take the same form. Okay, the quantity on this side is the linear quantity, and the quantity on this side is the angular quantity. Okay, when you have the omega become alpha, the v become at. But of course, for the acceleration, you have another component here. Okay, the centripetal acceleration. Now we would like to write the kinetic energy of a particle in a circular motion in terms of the angular velocity omega. Now, so the method is easy. You just change the v to r omega, right? This formula is correct no matter whether omega is constant or not. Okay, so that simply goes as half mr squared omega squared. Okay, that is the result. Now, but when we are doing with the rotation of a rigid body of a three-dimensional object, we may not have the motion confined to the XY plane. Now, for this example, for the example in the above figure, we have the motion confined to the XY plane, right? The circular motion is along in the XY plane of the coordinate system. But for a rigid body with certain heights, the rotation of the particles around the axis of rotation may not be confined to the XY plane. So it will be easier for us to deal with that situation by a small change in notation. We specify the axis of rotation like this. We call this a Z axis. And if there's a particle rotating about the Z axis in a circle with a radius of the circle equal to r pearl, then the kinetic energy is simply half mr pearl squared omega squared. Now, r pearl is the radius of the circle and is also the perpendicular distance of the particle from the axis of rotation. Okay, so they specify how large the circle is, right, about the axis. Okay, So we just replaced R, which is on XY plane, in general by the R pro, which is the perpendicular distance of the particle from the x-axis. So the particle may rotate in the circle that is lie above or below the XY plane. Okay. Now, so we are now ready to describe about the moment of inertia. Now, let's consider a three-dimensional object. I draw it as the cylinders for simplicity, but you can consider an object with an arbitrary shape. Okay, and the object is now rotating about this axis. Okay, with an angular velocity omega. Okay, now you should notice that the quantity omega is common to all the particles inside the object, because the omega is the angle turned about by the object per unit time, and that angle is the same for all the object, right? Now let's see. Let's draw a top view of this object. So this is the center of rotation. The axis of rotation is pointing out of page, right? Now along the radius of the rotating object, if you pick a particle here, it may have a certain speed I call v here, right? This is a linear speed, and the linear speed is of course perpendicular to radius. And at the rim of the circle, the linear velocity may be getting larger, right? Why is it so? Because the linear speed is related to the angular speed by r omega. Okay, so when you have different r, when you have different distance from the center, you have different linear speed. The speed of the particle will change when it moves along the radius. Okay, when you come from the circle, center of the circle, we have zero speed, to the rim of the circle, which has a larger speed of v equal to big R omega. Here we have the big R. This is the radius of the circle. So the linear speed gradually increased from the center of the circle to the rim of the circle. Okay, according to this relationship. But the omega remain constant. The omega is independent of whatever point you have in the circle, because it's the angle turned through by the particle, and all the particles share the same angle. Okay, if one particle turns by 30 degrees per second, and other particle and in other position of the disk also turn by 30 degrees per second. So that's why omega is a better parameter for describing the motion, because all the particles share the same omega. Okay, and that's why it's a small advantages to use omega but not v to describe the motion. Now, so when we want to describe the motion of the disk and write out its kinetic energy, we look at one particle at first, and this particle mi is at distance ri per from the axis, right? So its kinetic energy is half mi vi squared. And if I form a sum of all the particle kinetic energy, it becomes the object's total kinetic energy of rotation, right? So if I replace vi by ri per omega, it becomes something like this. Now, you notice that in the omega, I do not specify the I, because all the particles have the same omega. So I don't need to use a subscript to specify which particle's omega, right? So omega is a constant for the motion, right? It does not depend on I, okay? And that means in this formula, I can take the omega out. And the summation only acts on what? The summation is taken over the m and also the ri per square. So I now separate the kinetic energy into the product of two factors. The first factor is omega square, the square of the angular speed. Okay. Oh, sorry, this typo. The square of the angular speed. Okay. And the second quantity is a mysterious summation. it somehow contains the information about the mass distribution and the axis of rotation. So this quantity depends on how the mass is distributed and also the axis of rotation which you choose to rotate the object, right? So we nicely separate the kinetic energy into two factors. Okay, one factor depends on the object shape, depends on the object mass distribution and the rotation axis, and the other factor depends on how fast the object rotates. So I successfully separate the information about how fast the object rotates with the information about the shape of the object. Okay. And we define this summation as the moment of inertia I. Okay. Now, in defining this, I keep the subscript pearl because I want to remind myself that Ri pearl refer to the perpendicular distance of a particle from the axis of rotation. Now you consider these two particles. This is Mi, this is Mj, right? They are two different particles. Now, but Mi is closer to the axis of rotation. Mj is farther away, right? So they have different distance. For Mi, you have Ri pearl. Mj, you have Rj pearl, right? Now, but you can see these two distances are the radius of the circle, of the circular path they move. Okay, and it is a perpendicular distance from the axis, right? It is not the distance from a point, but it's a distance from an axis. Okay, so that's why I use the subscript pearl to remind me that. Okay, to remind me that it is a distance from the axis, the perpendicular distance from the axis. Now you can easily see that the quantity I depends on two factors. The first factor is how the mass is distributed in the object. The second factor is the axis of rotation. Okay. Now you see, I have a flask here, a flask, the object, the solid that takes the shape of a flask, right? So you can imagine if the flask is how do I say? If a flask is more extended in size, if flask is this point mass has a larger distance from the axis of rotation, then the summation will be larger, right? So it depends on actually how the mass distribute on the object. Okay, if you have a flask that is with a wider base, the distance of the particle from the axis will be larger, right? So the R per square will be larger, and the summation will of course be larger, right? And so the I will also be larger. Okay. And the second factor is the axis of rotation, how you rotate the object. Now in this diagram, I rotate an object about its symmetry axis, right? But I can do the other way around. I can, instead of rotating about the axis of symmetry, I rotate about the object along a horizontal axis. Or I can rotate the object about the axis tilted at an angle. Now you can see for these two axes of rotation, the Ri pearl or the Ri pearl will change because for Ri pearl I refer from the distance from the axis. Now the axis change, so all the Ri pearl will change, and the moment of inertia will be different. So that's why the I depends on the mass distribution and also the axis of rotation. You have to specify the axis of rotation in order for that quantity to be meaningful. Okay, so that's why we must specify the axis that you concern. Okay, when you want to find the moment of inertia. And from the formula, you can see that the unit for moment inertia is kilogram, the unit of mass. You have R per square, so you have the square of the unit of distance. You have a meter square, so the unit is kilogram meter square. And in terms of this I, you can now write the kinetic energy of a rotating body is half I omega square. Okay. Now, what is the advantage of doing so? You can see if I write the kinetic energy of a rotating body as half I omega square, then it takes the same form as the kinetic energy of the translational motion. You just replace the mass by the moment of inertia, and you replace the linear velocity with the angular velocity, and you translate the formula from the translational motion to rotational motion. So they are completely analogous to each other. Now, that similarity tempts us to identify any similarity in the concept of this quantity. Now, m in linear motion refers to the inertia of motion, right? The mass of an object is inertia to motion. And that means the reluctance of a body to change is translational motion. And that is Newton's second law. Newton's second law says the mass m of an object, it is reluctance to change the state of its motion, right? So the larger the mass m, the more difficult it is to change its motion. You need a larger force to change its motion, okay? So that means the mass is the inertia. And in fact, the moment of inertia I, it plays the same role for rotation. It refers to the reluctance of the body to change its rotational state. So if you find a body with a large moment of inertia, it means that it is very difficult to set it into rotation. Or once it is in a rotation, it is very difficult to slow down it and stop it. Okay, so that is the physical meaning of I. Okay, in the following discussion, we will find a Newton's second law in the rotational form. And at that time, it will be much more clear that the I actually refers to the inertia of a body to the change in rotation, change in rotational state. Okay. So this is the physical concept that you might like to memorize. Larger I is more difficult to make a body rotate. Now, the discussion so far is quite abstract. So let me begin with a very simple example consisting of 3 point masses. Now, this is a top view of a rotation. I suppose the axis of rotation is pointing out of page, and the 3 masses here are turning around that axis at different distance. The first mass is 1 meter, the second mass maybe 3 meters, the third mass maybe 2 meters. Okay, so I draw a table. Now I have to form a summation of the mass times the perpendicular distance square. Okay, so I label each of the mass. I label the 7 kilogram mass as 1. I label the 8 kilogram mass as 2. I label the 9 kilogram mass as 3. So the mass of respectively are M1 is 7, M2 is 8, and M3 is 9, right? And what are the distance from the axis? R1 pearl is 2, right? And R2 pearl is 3. R3 pearl is 1, right? So I write them down. And what is sorry, I have a typo here. It is MIRI pearl square. I missed a subscript. Please help me fill up. Now, so what is MIRI pearl square? It is the mass times the distance square. So 7 times 2 square, 2 is 4, 2 square is 4. So 7 times 4 is 28. And 8 times 3 square is x times 9 is 72. 9 times 1 square is 1. So 9 times 1 is 9. So I have MIRI pearl square here for the 3 masses. And the sum here means I add them up together. Okay, so adding up these 3 numbers will give me 109 kilogram meter square. That is the moment of inertia of the system about the axis. Is that clear? Now, I can also have a simple example of a dumbbell. Now, this so-called dumbbell is actually a 2-point mass attached to the end of the rod of length L. Okay, I have a light rod. The mass is negligible, and now I have 2-point mass, each of mass m, attached to its end. Now, suppose I can rotate this object by an axis that is passing through the end of the rod. Okay, I have the axis perpendicular to the rod and passing through one of the mass. So I call this axis A. But I can also rotate the object by an axis through its center. Okay, and I call this axis C. Do you know what I mean? Now, the moment of inertia, as I say, it depends on the axis. So if you choose different axes, you will be getting different numbers. Okay, and so I now have two moments of inertia. One moment of inertia corresponds to a rotation about axis A, which is at the end of, which is at the point mass. And the other moment of inertia, which I call IC, refers to the rotation of this object about the center of the rod. Okay, now let's see how to calculate it. Now for IA, the axis is there. So the first mass is located on the axis. So the distance between the mass and the axis is 0, right? So I have m0 square, okay, for the first mass. The second mass is there. It at a distance L from the axis. So a contribution is ml square, right? And the sum of the two is of course ml square. Okay. Now how about along the axis C? Now I find IC. Now about this axis, you can see each of the mass is at the distance L/2 from the axis. So this point mass contribute m multiplied by the square of the distance L/2 square, right? And the other mass also contribute by the same amount. Okay, so the sum of these two terms will give you half ml square. Now you can easily see that in this example, IA is larger than IC. Okay, IA is larger than IC. So what does it mean? It means that it is more difficult to rotate the object about the axis A than the axis C. Okay, now you can actually try this with a dumbbell. If you have a dumbbell at home, you try to hold the dumbbell at one end and try to rotate it. You will feel it's quite difficult to rotate it. While if you rotate the dumbbell at the midpoint, you hold the midpoint and rotate it, you will find it much easier. And it's because of this result, right? The moment of inertia about one end is larger than the moment of inertia about the center. Okay. Now again, we are interested in changing the calculation from a system of discrete point mass to a continuous mass distribution. This is important because most of the objects in our daily life, they are not made of discrete point mass, right? They are made of almost continuous distribution of mass. So in changing from the formulation from discrete point mass to a continuous distribution, we have to rely on the integration. Okay. Now let's take a simple example. Let's introduce this method by using example. I consider a uniform rod of length capital L. Okay. And the rod has a mass M, capital M. Okay. And now I want to find the moment of inertia of the rod about one of this end. Okay, the axis is now perpendicular to the length of the rod and is located at one of the end of the rod. Okay. Now suppose I now choose a coordinate system along the with the x-axis lying along the rod, and now I chop the rod into many small pieces. Okay, and for each of the pieces, I call it dx. A dx means a small increment in x. Okay, and that corresponding to a small pieces of the rod. And this small pieces of the rod is at a distance x from the axis A. along A, the X value is 0. So the X counts towards the right, like this, okay? Now I consider the moment of inertia. The moment of inertia is summation MRI per square, right? And for this segment, this small segment, there's a small amount of mass, delta M. So I have delta M multiplied by distance x squared from the axis, right? So I have delta M multiplied by x squared, xi squared, okay? And in a limit where there's this segment, the length of this segment becoming 0, the M, the mass will also becoming 0, okay? And so it becomes a very small amount of mass. And in the integration symbol, we denote the delta M by dm. So that the summation MRI per square integral summation now become R squared dm, okay? The integration of R squared over dm, okay? And dm, of course, I refer to the mass of the segment. Okay, the mass of the segment at a distance R squared from the axis. Okay. Now, how do we evaluate this integral? We know that the total mass of the rod is capital M. And when I divide it with the length of the rod, I get that the density is the mass per unit length, right? So M over L is the mass per unit length. So what is the mass in the segment delta D of length dx? Well, that is simple. I simply can multiply the length of the segment by the length density to get the mass dm. So dm is equal to the mass per unit length multiplied by the length of that small segment. Okay. So I successfully transformed the dm into a quantity that involves only x. Okay, so dm become m over l dx. And for this example, the r, the perpendicular distance, now become what? Now become the distance x. So r become x squared. R squared become x squared. Okay. And of course, I integrate from the axis to the other end of the rod, right? So I integrate from 0 to capital L. Capital L is the length of the rod. Okay. The constant can be taken out. So I'm left with the integration of x squared over x. And so I got x cubed over 3. And when I evaluate at the upper limit, I got L cubed over 3. Lower limit becoming 0. And I cancel one of the L. And that gives me 1/3 of ml squared. Okay, so that is the moment of inertia of the whole rod about 1n. Okay, and what I'm talking about is the rotation of a rod like this. Okay, it's a rod. Okay, I'm now rotating this rod about 1n. Okay, this is the axis of rotation. I'm now rotating the rod about this n, like this. So that corresponding to the moment of inertia. Okay, the inertia which I can rotate about the rod above 1n. Okay, that is the idea. Now, so let's continue. Yes. Now, before having the break, let us prove an important theorem of the moment of inertia, and that is called the parallel axis theorem. Now, you may be scared by these pages, which looks very complicated, right? The proof is actually very complicated, but don't worry, I would not teach you, I would not test you how to prove this in your final exam. Don't worry about that. But first, I would like to introduce what is the parallel access theorem. Okay, and all you need to know is how to apply the parallel access theorem to different situations. And that's what I will test you in the final exam. You will not be required to do this proof. Don't worry about that. Okay, so I better tell you the result first, and then I go back to the proof. Okay. Now, the parallel access theorem says so. If you have an object, a three-dimensional object, for example, like this, of course, you have the position of the center of mass. I call the center of mass position Cm, right? Now consider two parallel axes. Okay, one axis I call C is an axis that passes through the center of mass of the object. Okay, so that's why I call it C. The other axis I call A is an axis that is parallel to axis C, right? But it is a distance from the center of mass. It is a perpendicular distance r pro. So this r pro is the distance between the two axes. Okay, one axis C is passing through the center of mass. The axis A is not passing through the center of mass, but at the distance r pro from axis C, and the two axes are parallel to each other. Okay. Now, so I would be able to get a simple relationship between the moment of inertia about A and the moment of inertia about C. IA and IC, they are simply related by this formula. IA is equal to IC plus what? Plus the total mass of the object multiplied by the square of the distance between the two axes. So it's mr per square. So this relationship is simple. So that means what? That means once, if you, for example, if you find the moment of inertia of an object about an axis through the Cm, you will be able to find the moment of inertia of the same object about any other parallel axis, as long as you know that the distance of that axis from the center of mass. Okay, so you simply add the term of mr per square, you get the moment of inertia at any other parallel axis IA. Okay. Now that also tells important something interesting. You know that notice that IA, because the mr per square is always positive, right? The r square is a positive quantity, m is also positive. So that means IA is larger than IC, always larger than IC. So that means what? That means among all the parallel axes, okay? Among all the parallel axes, the moment of inertia about and the axis that passes through the Cm is the minimum. Okay, so the axis about Cm has a minimum moment of inertia among all the axes that are parallel to it. Okay, so and that is an interesting observation. Now let's go back to the proof. Now this is a horrible thing. Now I draw an axis A and axis C like this, and I draw a vector from a point on axis A to the point on axis C. I call this vector R pearl vector. Okay. Now this vector is perpendicular to both axes. Okay. So I draw a green square to denote that this vector is perpendicular to both axes. Now I consider a general point in the object, which I call the mass Mi. So the perpendicular distance from axis A, I call it Ri pearl, and I denote it by a vector that points from axis A to this mass. And the distance of the mass from the axis C, I denote it by Ri pearl prime. Okay, the vector that points from axis C to the mass. Okay. Now this diagram is a three-dimensional diagram, right? if you take a look at the object from the top, you imagine now I'm at the top, I'm somewhere here, and I look downwards. Okay, these three vectors, Ri pearl prime, and capital R pearl, they form a triangle, right? Is that right? They are not lying on the same plane. They may not lie on the same plane. But if you look at it from one dimension, two dimension, they just form a rectangle triangle. Okay. So the three, you can see the three vectors, they are related this way. Okay, the mass Mi is here. This is Ri pearl, this is Ri pearl prime, and this is capital R pearl. Okay. Now, first we take a look at the moment inertia about axis A. It is of course given by the standard formula, Mi Ri pearl square. But Ri pearl square, I can make use of this triangle to express Ri pearl in terms of the prime quantity and the capital R, right? You can see Ri pearl vector, this vector, is equal to Ri pearl prime plus capital R pearl. A simple vector addition, right? Between this vector and this vector will give you this vector. Okay, so I can now replace the Ri pearl with capital R pearl plus Ri pearl prime, and I take the square of it. Okay. Now, if I square the vector, that means I form a dot product of the vector with this cell, right? So I got three terms as usual. The first term is R pearl square, capital R pearl square. The second term is Ri pearl prime square, right? And there's also a cross term. The cross term consists of a dot product between these two vectors. So I have 2 times capital R pearl dot with small Ri pearl prime. Okay, so that's the these are the 3 terms. Now the summation can be distributed to each of these terms, right? So for the first term, I have summation Mi. R pearl square is a constant, so I can take it out for summation. The last term is summation Mi Ri pearl prime square, right? Now I can easily see that this term is just capital M multiplied by R pearl square, because summation of all the mass is the total mass of the system. So summation Mi is just capital M. And the last term here is just what? It's just the moment inertia about the axis C, because I now have summation Mi Ri pearl prime square, right? That is the definition of the moment inertia about axis C. So essentially, I got the result. But still, I have to prove that the summation of the middle term, the dot product term, is equal to 0. Okay. Now, how do I do this? Because I know that the capital R pearl is a constant, so it can be taken out of the summation. So the summation goes with what? The summation goes with the Mi Ri pearl prime. But when we discuss about the moment of inertia, about the center of mass concept in the last chapter, we already have shown that this is equal to 0, because you see now every vector that points to the mass, it begins at the center mass position, right? This Ri pearl prime, they all begins with the center mass position, pointing outwards to different masses, right? So that means the summation of Mi Ri prime is equal to 0, as shown in the last chapter, right? You take the moment about the center of mass, and that of course gives you 0. Okay. Now, although I take the perpendicular component, but in general, this relationship is true even for 3-dimensional. Now I just take the perpendicular component, and this equation will still hold. Okay, because this is a vector equation, so the all the 3 components of the vector will obey the same result. So I take the perpendicular component, and it's still true. So that means this term is equal to 0. And I got my result already, right? IA is equal to M capital R per square plus IC. Now for the application of this formula, I better take a break now, and I will introduce you in the second part of the lecture. Okay, so let's take a break for 10 minutes. Now let me turn on the recording. I share the screen. I share this slide for you. Now let's look at this. Now this is a continuous distribution, right? This is a continuous distribution. Now I divide this this continuous mass distribution into many small pieces. Okay, into many small pieces, and the mass of the pieces of the I pieces, I call it delta Mi. Okay, delta Mi stands for the mass of the I pieces, and because eventually I will let the pieces to be very small, I will consider a lot of those pieces. I will divide the solid into infinitesimally large number of pieces. Okay, infinitely many pieces. So the mass of each pieces will eventually turn to 0. So that's why I use delta M to denote the mass of each pieces. Okay, this is a small pieces. Eventually, the mass of that pieces will go to 0. And by our formula, I is summation M Ri per square. Now my M is small, just this a little piece. So I have delta Mi Ri per square. Okay, can you see that? Now, if you consider the limit where I divide it into infinitely many small pieces, then the mass of each pieces will go to 0. The delta Mi will tend to dm. Is that right? It will tend to dm. And so that means this summation will go to Ri per square dm. The d will go with the m, but not the r. Is that right? Okay. Can you do you understand this explanation? Do you get it now? Yeah. That is the why. Now I will modify my PowerPoint a little bit, and I will post it in the web. Okay. This point is important. So thank you very much for raising this point. I think I need to explain more to the other students as well. Okay. Now let us use the parallel access theorem now. Now the parallel access theorem says so. IA is equal to MR per square IC. Now I have a rod. I have a rod like this, a uniform rod like this, and I already have found the moment of inertia of the rod about 1n. Okay. In a big example, I use integration, right? And it is equal to 1/3 ml squared, where L is the length of the rod. Is that right? Now I want to find the moment inertia about an axis C, parallel to axis A, but passing through its center of the rod. Okay. So what is IC? Can you use the parallel access theorem to help me find out? I give you 2 or 3 minutes to find the answer. Yes. Another question? Yeah, you got it right. You got the factor 1/12 ml squared. That's correct. Yeah. Any other student have got the answer? Now the idea is easy. The idea is not difficult. You already know this, right? You already know this as 1/3 of ml squared. Now you want to find IC, right? And what is this? The total mass of the rod multiplied by, now, don't remember the symbol. Remember the meaning of the symbol. The capital R per is the distance between the two axes, right? The distance between the two axes. Now the distance between the two axes is what? Is alpha 2, because the total length of the rod is L. So this distance is alpha 2, right? So what I'm going to do right here is M multiplied by L over 2 square, right? Because R per is alpha 2 now. Is that right? So the answer is easy. IC is equal to 1/3 of ml squared minus what? Minus 1/4 of ml squared. So you get 1/12 of ml squared. So that's the answer. Now, of course, you can use integration to find out the same answer. Okay. Now, in our calculation here, we use integration, right? From 0 to L, right? To do this integration. Now, I can do the same integration sorry, I missed an example, a pure example, but I will go back. Don't worry. Now I can use the same integration, but to find IC. Now again, I integrate R squared dm, right? And as we found, dm is L over big M over L dx. The R is now, of course, x squared. But if I take the origin to be along axis C, okay, this is x, right? Then the integration of x will go from what? Will go from here to here, right? Will go from minus alpha 2, which is the left end of the rod, to plus alpha 2, which is the right end of the rod. Okay, if you do this integration, you do it carefully at home, you will find that it's exactly 1/12 ml squared. Okay, so of course you can use the integration to do it. Okay, and that produces the same result as we did with the parallel axis theorem. Okay. Another simple example is this. We've already found that, for example, if we have this dumbbell problem, right? And we have found the moment inertia about axis A and axis C respectively, right? Now suppose we know IC. IC is given by the moment inertia about axis C is given by half ml squared. And we are going to use the moment, the parallel axis theorem to find IA, the moment inertia about axis A. Okay. Now IC is what? Is half ml squared, right? It is the moment inertia that passes through the center of mass, right? That is given. And then the distance between the two axes is now alpha 2. So the capital R per become alpha 2 square. Now you should know that the M here should be careful. The M here refers to the mass of the system. The mass of the system, not just the mass of one of this, right? So the total mass of the system is 2m. Okay, so it's 2m multiplied by alpha 2 squared. And if you add this to this, you got ml squared, right? And that's exactly the result you got in our previous example. In our previous example, we actually work in a fundamental way to find out IC and I respectively. Now you can see they are just related by using the parallel axis theorem. Okay. Now we introduce another important theorem in moment inertia, and that's called the perpendicular axis theorem. Okay. Now the perpendicular axis theorem does not apply to a three-dimensional object. It only applies to a laminar Now, what I call lamina is an object which is two-dimensional. Essentially, the object is so thin that we can neglect its thickness. We can neglect the thickness of the object compared with the size of the object. Okay, and so that's why and that's called a lamina. Okay, 薄片啊，一塊好薄嘅薄片啊，嚇。We place the lamina in such a way that the surface of the lamina now lies on the XY plane. So the XY axis are both parallel to the lamina. Okay, and the Z axis is now perpendicular to the lamina because the Z axis is perpendicular to the XY axis, so it's perpendicular to the lamina. Okay, so what we are going to find is a relationship between the moment inertia of the object through the three axes, Ix, Iy, and Iz. Okay, so we're going to find the relationship between the moment inertia of the object about these three mutually perpendicular axes. Now, first I consider Iz. Iz is the moment inertia about the perpendicular axis, right? The axis that is perpendicular to the surface of the object. And so that's given by summation mRi per square. This is our standard formula. Now, but be careful. You can see in this formula, we have what? We have Ri per square, which is the distance between the point mass Mi and the axis. Okay. And so in this diagram, if my point mass is here, then Ri per square is this distance. Is that right? Now you are required to find Ri per square, the square of this distance, to calculate the moment of inertia. But you can always express Ri per square in terms of is the x coordinates, the x coordinate and the y coordinates of this point mass, right? The x coordinate is of course xi square, xi, the y coordinate is yi. By Pythagoras theorem, the Ri per square is xi square plus yi square. I consider this right angle triangle. Ri per square is xi square plus yi square, right? So I can separate the summation into two terms. The first term is summation mi xi square, and the second term is summation mi yi square. Okay. Now let's be careful. What is xi? Xi is actually the distance, the perpendicular distance of this point from the y-axis. Because this is xi, right? This length is xi, the x-coordinate of the object. But the x-coordinate of the object is distant from the y-axis. So if I form a summation of all the mi xi square, it becomes iy. Because this xi now is the perpendicular distance from the y-axis. So that means if I form a summation of this thing over all the particle, I got iy, the moment inertia about the y-axis. And on the other hand, look at the yi here. Yi is this distance. It is a distance of the point mass from the x-axis. So that means if I form a summation of all the mi yi square about the of the object, I will arrive at the moment inertia about the x-axis. Okay, so you see the label x and y actually they reverse. Summation m x square give you the iy, while summation m y square give you the ix. Okay, so a little bit confusing, but after you understand the physical meaning, you will be able to figure out it out without difficulty. So that's why I always remind you not to memorize the formula itself. You memorize the physical meaning. Okay, when you realize that the physical meaning of this Ri per square means the perpendicular distance from the axis of rotation, you will easily identify this term and this term to be Iy and Ix respectively. Okay, you will not confuse them. Okay. So now we have the perpendicular axis theorem. The perpendicular theorem says that the moment inertia about the three axes are related this way. Iz is equal to Ix plus Iy. Okay, now but that's applied only to a lamina. That cannot be applied to an extended object. I must warn you again and again. You cannot apply that to a three-dimensional object. You can only apply it to a object that lies on the plane. Okay. And also the Z axis is the axis that is perpendicular to the plane of the object, while the X and the Y axis are the axis that is parallel to the surface, the plane of the object. So the meaning is like this. IZ, I consider an object rotating about the perpendicular axis, while IX and IY, I consider the object rotating about and at the two axes which are along the plane of the object. And all these three axes are perpendicular to each other. Okay. So IZ is equal to IY, X plus IY. Now let's apply this perpendicular axis theorem to a point mass distribution. Now I consider a circle of radius R, capital R, and the circle now lies on XY plane. The circle is now is not a continuous one, but it consists of point mass distributed evenly on the circle. Okay, now, how many point mass I don't know. I only know that they are point mass, and they distribute symmetrically about the x-axis and the y-axis. That's the only thing I know. Okay, and if I sum up the total mass of this point mass, I find that the total mass is capital M. Now, even though I don't know how many masses are there, and I don't know the respective angle between the two masses, I don't know this information, I still can calculate the moment inertia of the configuration about the X, Y, and Z axis. Now that sounds quite counterintuitive, but let's see how we do it. Now, first we consider the moment inertia about the Z axis, which is pointing out of the page. Now, if you consider Z axis, you can see all these point mass, no matter where they're located, they are all at equal distance from the axis. And that distance is of course what? It's of course the radius of the circle, because they lie on the radius of the circle. So the distance from them to the axis is of course the radius of the circle. So all the Ri pearl is just equal to capital R. They are all equal to capital R. Okay. So the summation mi R pearl square is just summation mi capital R square. And that is of course summation mi multiplied by R square. Summation mi is capital M. So IZ is just mr squared. Okay. Now, but as I say, the distribution had the same distribution about the X and the Y axis. Okay. If you look at the distribution about the Y axis, and if you look at the distribution of the X axis, they exactly look the same. Okay. So that means Ix is equal to Iy by symmetry. Okay. And by the parallel axis theorem, by perpendicular axis theorem, we have IZ equal to X plus Iy, but X and Iy are equal. So that means X and Iy are each equal to 1/2 of Iz. And that means it's equal to 1/2 of mr squared. Okay. Now, so you can see I can find X and Iy easily, even though I don't know how many masses are there, and the actual angular distribution doesn't matter. Okay, I can easily find the moment inertia by the perpendicular axis theorem. Okay. Now let's try a slightly more difficult example. Consider a disk, a uniform disk with negligible thickness. So it's a circular, so to speak, a circular lamina. Okay, or you can say a uniform disk. And the disk has radius capital R, and the total mass of the disk is M. Now, I want to find the moment inertia of the disk about the Z axis. The disk lie on the XY plane. I now want to find it about a perpendicular axis perpendicular to its plane and passing through its center. Okay. Now, how do I do it? What should I do with an integration? I integrate R squared dm to be more correct, should be R pearl square. Okay, R pearl square dm, where R pearl is the perpendicular distance from the axis. Now, how do I cut this object, right? In doing integration, I'll always have to cut the object into pieces. Is that right? How should I cut it? Now, I should cut it in a way such that all the masses on the pieces will have the same distance from the axis. So I can define the R pearl correctly. And that, of course, can be done by considering a ring with a small thickness, okay, on the disk. Okay, so I consider a ring that extends from radius R to radius R plus dr. Okay, so the thickness of the ring is dr. Okay, I consider this ring. And you can see all the points on the ring, because the thickness is so small, all the points on the ring have the same distance r from the center, from the axis of rotation. Okay, so that becomes a well-defined R square. The difficult thing now is how to find the dm. The dm is what? The dm is the mass of each pieces. And in this case, now I chop the disk into a lot of rings. So the dm become the mass of the ring. Okay, how do I find a mass of the ring with a small thickness dr and radius r? That's my problem. Okay, now that's not so difficult. The first step is to find the mass density. The density is the mass per unit area. The total mass is m, and that mass is distributed over the surface area. So I divide the mass by the surface area of the circle, I get the mass per unit area. And of course, for a circle, the area is pi r square. So the density is m over pi r square. Okay. Now, in order to find the mass of the ring, I need the area of the ring. The area of the ring I can find easily because the ring is so thin. So I can just multiply the circumference of the ring by the thickness of the ring to get the area. Okay. So the circumference of the circle is 2 pi r, and the thickness of the ring is dr. When I multiply them together, I got the area. So if I multiply the area of the circle of the ring by the area per mass per unit area, I will get the mass in the ring. Okay. Okay. Is that clear? Now you may not like my argument. You may say, well, the circumference have a different from the inner and outer side. They are not the same in the inner side and the outer side. So how can you say it's 2 pi r multiplied by dr? How can you use this product to find the area? Now I can do it another way. Suppose I now have a circle. The circle has a radius r, okay? And I now consider a small change in the radius, which I call dr. So the circle will go to a larger diameter radius, right? And I would like to consider the area change. Originally, the area is A. And if I extend the circle by increasing its radius r, the new area is dA, right? The increase in area is dA, which corresponds to the area of the ring. So I can use the differentiation to find dA. Because I know the area of a circle is pi r square. So a small change in area that corresponds to a small change in r can be found by straightforward differentiation. dA is equal to pi dr square. But dr square is 2r dr, right? So I have 2 pi r dr, which is exactly the same as this one. Okay. Now, so you can use whatever method you like. As long as you get the result correctly, that method is going to work. So I have everything ready now. I multiply the area of the ring with the density. I got the mass, dm. So I put it back here. And r is, of course, the radius of the ring. So I can integrate. I integrate from the axis to the rim of the circle. So I integrate from 0 to capital R. Now you see, I have a small r square here. I have another small r here. So I integrate R cubed from 0 to R. Okay, the constant are taken out. The pi cancel, and I've tidied up some constant. I get something like this. Integrating R cubed become R to the power 4 divided by R, but divided by 4. You very upper limit, it become R to the power 4, right? And after canceling the R square and canceling a factor of 2, I get 1/2 of mR squared. So that is the moment of inertia of a disk about its symmetrical axis at the center. Okay. Now I can take a step further to find the moment inertia about the x-axis and y-axis, which are on the plane of the disk. Okay, and that relies on the perpendicular axis theorem. I know that Ix is equal to Iy because the distribution is the same about the y-axis and about the x-axis. So I'm sure that these two I are the same. But Iz is equal to Ix plus Iy. I know Iz already, right? So h of Ix or Iy is equal to half of Iz, and this half of half mR squared, and that means equal to 1/4 of mR squared. Okay. Now remember, the moment inertia of the body always take this form. Okay. Because the dimension of the moment inertia is the mass multiplied by what? Multiplied by the length square. Because I have summation, right? I always have the moment inertia given by summation I mi ri per square. I already have this, right? So is it length? The length? Sorry, this is mass multiplied by a length square. Okay. After you do a summation, the dimension is still unchanged, right? The dimension is unchanged. So you get a mass multiplied by a certain length square. And that's typically what you expect from the moment of inertia. Okay. Eta is the numerical constant. L is a typical dimension of the object. And for a circle, that is a radius. And for a square, that may be the side of a square. And also for a rectangle, that may be a length or width of a rectangle or a combination. Okay. And it depends on typical length scale of that object. The mass is the total mass of the object, and eta is a dimensionless number. And in order to find out that number, you have to rely on integration. Okay, if you have an object of different shape, then you have to rely on integration just to find out this number. Okay, and in our previous example, we see that for rod, let me summarize a bit. For a rod about 1 n, it is 1/3 of mL squared, right? And in our previous example, we find what? A disk, right? A uniform disk about symmetry axis. And that's half mL squared. So in this case, for the rod, it's 1/3 about 1 n. This eta factor is 1/3. And for this about its symmetry axis at the center is 1/2 of mR squared. Okay. So this constant you have to find out by using integration or by applying the parallax and the perpendicular axis theorem. Okay. So that's the idea. If you got an answer that is not of this form, you must have done something wrong. So you better go back to check the answer. Okay. Now here is an classwork. In our previous chapter, we already have considered uniform semicircular disk. The disk has a radius r and mass m. Okay, radius r and mass m. And here I have already found in the previous chapter. I found the center of mass position. The center of mass of the semicircular thing is at the height of capital Y above the x-axis. And capital Y is, I find 4r/3 pi. That is the result from our previous example. Okay. Now I'm going to find two things. The first thing is, if the lamina now lies on the xy plane with the base coincide with the x-axis, then what is the moment inertia about the z-axis, which is pointing out of page? That is the first question. The second question is, what is the moment inertia about an axis that passes through the center of mass of the object, but perpendicular to the plane of the lamina? Okay, now let's answer the first question together. What do you think? What do you think is the answer? I'm now considering this point, this axis. What is the moment inertia of the semicircular thing about this axis? Any suggestion? Now, we already have found for a full circle, the moment inertia about the axis at the center is what? Is half mr², right? So for half of the circle, you may be tempted to reduce the mass by half. Now, the upper part, if you divide the circle into two halves, because the moment inertia is a summation, right? The upper half of the circle and the lower half of the circle, they contribute the same amount to the moment of inertia. So you may be tempted to write the moment of inertia of a semicircle to be like this, right? But that's wrong. Why? That's a little bit tricky because you now define the mass of this thing to be m. While in this case, you define the total mass of the circle to be capital M. So if you are now referring to the mass of the semicircle as m, there's actually no such m/2 factor. The answer here is simply half mr², just like what you have for a full circle. Because the definition of m is defined differently here. The m here refers to the mass of the semicircle, but not the full circle. Okay, so for the same mass distribution, you still got a half mr². Okay, and so the second question now, what is the moment inertia? Now I have IEZ equal to half mr². So what is the moment inertia about the center of mass, ICM? What is that? Somebody asked me 1/2 of the full. You think about it. the problem is not that you are wrong, but we are defining the mass in a different way. Now let me explain to you a little bit more. Now this point is actually not unimportant, but you may run into this mistake frequently when doing homework. So I explain a little bit more. Suppose now I have a full circle, and I call the mass of this circle to be m prime. Okay, and I asked you what is the moment inertia of the full circle about the center. Then of course you have m prime r², right? Is that right? Now I divide the circle into two halves, and I asked you about the moment inertia about 1/2 about the center. Then of course you have what? You have m prime over 2 r², right? But now if I redefine the mass of half a circle as m, if I define m power 2 as m, that becomes what? That becomes half mr², just like a full circle. The problem lies with the different definition of m. It's just because of the m is defined differently in the two problems. Okay. Now, for the moment inertia about the CM, ICM, I apply the para-axis theorem is equal to IA, as far as I remember, minus M R per square, right? The MR per square always goes with the CM as a plus sign. If you move it to this side, it becomes a minus sign. Now, in maybe I should write this. Maybe I should write IZ because I refer to this as a EZ, moment inertia about EZ axis. So this is IZ. IZ is known, half MR square, right? Now the perpendicular distance between two axes is half of my square, where y is given by this guy, right? So what does it become? I extract a factor of mr square out, and it becomes what? It becomes 1 here minus the big Y square divided by R square, and the big Y square divided by capital R square is just 4 over 3 pi square. So that's my answer. Okay, is that okay? Now, if you want to learn more about the para-axis theorem, perpendicular axis theorem, you can look at this e-learning module. Okay, encouraged to learn more. Now, in the next lecture, we will discuss about the Newton's second law for rotation. Let's have a brief introduction to you first, and we will discuss in more detail in the next lecture. Now, let's compare the linear motion of the rotational motion. We always do this, right? For the linear motion, we have x as the position. For the angular motion, we have theta. For linear motion, we have the velocity, the linear velocity. Now, for the rotation, we have angular velocity omega. And the linear acceleration now becomes the angular acceleration. And for the inertia, we have the mass for the linear motion is the inertia to the motion. The reluctance of the object to change its state of linear motion, right? So the mass is m, and the reluctance of a body to change its state of rotation is the moment of inertia. So m now corresponds to I for the rotational case. But we also have the force for the linear situation. The linear situation is the force. So what corresponds to the rotational form of the force? I would suspect that there's a quantity there that corresponds to the rotational counterpart of the force, and that quantity is a torque. It's a torque. Torque plays the role of force in rotational motion. But how do we define the torque? Now, the torque is no mysterious thing. It is just the moment of force you learn in high school. Now, remember what you learned in high school? In high school, when you say you turn an object, you apply a force to turn a door. For example, this is a door. This is a hinge of a door, right? This is a force. How do you calculate the moment? The moment is a force multiplied by the perpendicular distance. The force times the distance gives you the moment. Now we call it a torque. Okay, torque is just a more sophisticated name for the moment of a force. Okay, so we write torque here. Now we use the definition of energy consideration, right? We know that if my object is under the motion, if it's in a linear motion and it moved by a small distance delta x, the force will do a work on it, and that's given by F delta x. Okay, so delta W is equal to F delta x for the linear case. Now we suppose a similar thing happens. We suppose if an object rotates by a small angle, which is delta theta, and the object is under the action of a torque, then the work done will be equal to torque multiplied by delta theta. Now we define the torque in this way. Okay, And then how would it be? Eventually, we will find that the torque is exactly what we got, F per multiplied by R. Let's see why. Now we consider a force acting on an object in rotation about the origin O, and the rotational radius is R. So the force acts in this direction. And the force has two components, right? One component is parallel to the radius, which I call F parallel. The other component is perpendicular to the radius, which we call F per. Now parallel and per refers to the force component parallel to the radius and perpendicular to the radius. Now what is the work done? The work done, because the particle is moving along the circumference of a circle, so in a small time delta t is just moved through a small angle, and the distance is the radius r multiplied by the angle delta theta. So this is delta s. And only the component of force that is tangential to the circle will do work. The component of force of the force parallel to perpendicular to the tangent parallel to the radius, it will not thus work. So the work done will be F per, the perpendicular component of the force, multiplied by delta S. Okay, but delta S is R delta theta. Okay, so if I combine the F per and R, I define it as torque, then the work done will become a torque multiplied by delta theta. Okay, so we define the torque this way. We define the torque as a perpendicular component of the force multiplied by the distance from the rotation axis. Okay, so you can see in this way we define the torque with this formula, and the torque has a dimension of the unit of force multiplied by the unit of distance. So it has a unit of Newton meter. Okay, now you can see Newton meter is exactly the unit of work, because the angle, it carries no dimension. Delta theta, when expressed in radian, is carrying no dimension. So that means the dimension of the work done is the same as the dimension of torque, and that's the same as the dimension of energy. Okay, so all the dimension of the work, energy, and the torque, they're the same. Now, in the next lecture, we will derive the equation of motion, the Newton's second law in a rotational form, using this torque, and we will find exactly what we expect. We will find that eventually we will find that the torque is equal to the moment inertia multiplied by the angular acceleration, just like Newton's second law. Newton's second law says F equal to ma for a single particle, right? Now the A become the alpha, the M become the I, and we can see that the F now actually become the torque tau, right? This is what we expect, and we are going to prove it in the next lecture. Okay, so let's stop here. We have a long lecture already.